Can civilizations eat black holes? Tonight, we're going to explore the most mind-bending possibility in the cosmos. Civilizations so advanced, they harvest energy from objects where reality itself breaks down. You've probably heard about black holes in documentaries and movies, but here's what most people don't realize. These cosmic monsters aren't just destructive forces, they're the ultimate power source. A single stellar black hole produces more energy than 100,000 suns combined. By the end of this journey, you're going to understand exactly why the most advanced civilizations in the universe would inevitably turn to black holes, and how they might build megastructures that make our wildest science fiction look primitive. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. You probably poured yourself a cup of coffee this morning. The steam rose gently from the surface, curling in patterns that disappeared as quickly as they formed. You stirred it, perhaps with a metal spoon, watching the liquid swirl in a miniature vortex before settling into stillness. It was warm, it was familiar, it was home. But imagine, for just a moment, that the energy heating your coffee didn't come from electricity generated by burning coal or splitting atoms. Imagine that somewhere, impossibly far away, a civilization had learned to harvest power from the edge of a black hole, that warped region where space itself breaks down, and somehow transmit that energy across the cosmos to warm your morning ritual. The same force that can tear apart stars, focused and controlled, bringing gentle heat to your kitchen table. This isn't science fiction. This is a thought experiment about what might be possible when intelligence evolves far beyond our current understanding. When civilizations learn to work with forces that operate on scales so vast, so extreme, that our entire planet would appear as nothing more than a speck of dust drifting in an ocean of possibility. Right now, as you read these words, there are objects in space so dense that a teaspoon of their material would weigh as much as Mount Everest, so gravitationally intense that they bend light itself into spirals, so energetically powerful that they can accelerate matter to nearly the speed of light and hurl it across distances that span entire galaxies. These are black holes, and they represent something that challenges the very foundations of how we think about reality. The concept we're about to explore, civilizations that might harness these cosmic monsters, represents the absolute limit of what human imagination can grasp. It's like trying to explain the internet to someone from the 18th century. They might understand individual words, but the complete picture would remain fundamentally incomprehensible. The gap between their reality and ours would be smaller than the gap between our reality and what we're about to consider. Your brain didn't evolve to think about black holes. Over millions of years, your ancestors developed neural pathways optimized for tracking objects the size of fruits, predicting the behavior of animals during hunts that lasted hours or days, navigating landscapes measured in kilometers. Your deepest intuitions about physics come from throwing rocks and climbing trees. Even your most abstract mathematical thinking ultimately traces back to counting objects you could hold in your hands. But black holes operate on scales that have no equivalent in human experience. They concentrate mass equivalent to multiple suns into spaces smaller than cities. They create gravitational fields so intense that they're literally 100 million times stronger than what you feel standing on Earth right now. The numbers are so large that they cease to have meaning in any tangible sense. Think about this for a moment. A single stellar black hole, not even the largest type, just a typical one, contains about 10 times more matter than our entire sun, compressed into a sphere with a diameter smaller than Manhattan. The gravitational pull at its surface is so extreme that if you could somehow place your head just a few meters closer to it than your feet, the difference in gravitational force would stretch your body like taffy until your atoms themselves came apart. This isn't dramatic exaggeration. This is the measured, calculated reality of these objects. Yet perhaps, like an ant walking across the surface of a skyscraper without comprehending the architecture surrounding it, civilizations might learn to navigate these impossible environments. The ant doesn't understand steel and glass and elevators, but it can still find paths through the structure. Maybe intelligence, given enough time and evolution, could develop ways to work with forces that currently seem utterly hostile to life. Because here's what drives the possibility: energy. Every civilization that has ever existed has been defined by its relationship with energy. Hunter-gatherers burned wood and consumed food that stored solar energy through photosynthesis. Agricultural societies learned to harness wind and water. Industrial civilizations discovered coal, then oil, then nuclear fission. Each leap in energy utilization corresponded to a fundamental transformation in what that civilization could accomplish. Today, human civilization consumes about 18 terawatts of power continuously. Imagine 18 trillion light bulbs burning constantly across the entire planet. But even this enormous consumption represents only a tiny fraction of the energy that flows through natural systems. The sun bathes Earth with 174,000 terawatts of energy, and we capture less than 1% of 1% of it. A civilization truly advanced beyond our current level wouldn't just need more energy than we use today. They would need energy sources that dwarf our comprehension. Millions or billions of times more powerful than anything we've yet imagined. And where might such energy come from? From the very objects that seem most hostile to life, from black holes themselves. Consider what happens when matter falls toward a black hole. As material spirals inward, it accelerates to incredible speeds and heats to temperatures of millions of degrees, glowing brighter than the cores of stars. This swirling disk of superheated matter can radiate energy at rates that make our sun look like a dying ember. A single stellar black hole, actively feeding on material from its surroundings, can outshine 100,000 suns simultaneously. But there's something even stranger than the raw power output. There's time itself, near a black hole. Time behaves in ways that make science fiction seem conservative. If you could somehow survive close to the event horizon, that invisible boundary where even light cannot escape, you would experience time flowing normally from your perspective. But to someone watching from a safe distance, you would appear to slow down dramatically. An hour of your subjective experience might correspond to years or decades for the outside observer. This isn't speculation. This is direct consequence of Einstein's equations, confirmed by every experiment we've been able to devise. Gravity doesn't just bend space, it bends time. And near black holes, this effect becomes so extreme that it transforms any potential civilization into involuntary time travelers, operating on completely different temporal scales than the rest of the universe. Imagine trying to coordinate a civilization where some members experience years while others experience centuries. Where a conversation between different groups requires planning across geological timescales. Where the very concept of simultaneous action becomes meaningless because simultaneity itself breaks down in extreme gravitational fields. The astronomer Nikolai Kardashev proposed a way to classify civilizations based on their energy consumption. Type 1 civilizations harness all the energy available on their home planet, about 10 or 16 watts for an Earth-like world. Type 2 civilizations capture the entire energy output of their host star, roughly 10-26 watts for a sun-like star. Type 3 civilizations control the energy of an entire galaxy, approximately 10 or 36 watts. Each jump represents an increase of 10 billion times more energy. Each transition would require technological capabilities that are virtually impossible to imagine from our current perspective. We are currently somewhere around Type 0. Is 7 on this scale. We can't even fully harness our own planet's energy resources, but even Type 3 civilizations might find themselves constrained by the fundamental limitations of stellar energy. Stars are wonderful, but they have limits. Our sun produces about 4×10⁻26 watts through nuclear fusion, converting hydrogen to helium in its core and radiating the energy away as light and heat. This process will continue for roughly 5 billion more years before the sun exhausts its fuel and begins to die. A black hole of similar mass could potentially produce 100,000 times more energy through the processes occurring in its accretion disk. And unlike a star, which has a limited fuel supply, a black hole could theoretically continue producing energy for trillions of years as long as material continues to fall into it. The physics involved pushes beyond anything we understand intuitively. Near these objects, the normal rules break down completely. Space and time become intertwined in ways that our everyday language cannot adequately describe. Matter behaves according to principles that seem to violate common sense. Energy and mass become interchangeable in ways that Einstein predicted, but that still feel magical even to physicists who work with these concepts daily. It's like living on the surface of a calm lake, unaware that beneath the placid water lies an ocean of incredible depth and complexity. Most of the time, the surface gives us everything we need to understand our immediate environment. But black holes force us to acknowledge that we're floating on something much deeper and stranger than we typically consider. We can imagine spaceships and space stations. We can envision colonies on Mars or vast cities floating in space, harvesting energy from fusion reactors or solar collectors. These concepts stretch our technology, but they don't fundamentally challenge our understanding of what's possible. They operate within familiar paradigms, using familiar physics scaled up to larger sizes. But civilizations that extract energy from black holes would operate beyond our terrestrial paradigms entirely. They would need to solve problems we can barely formulate, work with materials that don't exist under normal conditions, and coordinate activities across timescales that span millions of years. Every aspect of their existence would be fundamentally alien to our experience. The Hubble Space Telescope has already given us glimpses of how extreme these environments can become. It has observed jets of material streaming away from black holes at 5% of the speed of light, matter accelerated to velocities that our most powerful particle accelerators can barely approach, sustained across distances measured in light years. These jets carry more energy than billions of stars combined, creating structures that dwarf entire solar systems. And yet, any civilization attempting to harness such power would face challenges that make our most difficult engineering projects seem trivial. The radiation environment near black holes would instantly sterilize any biological life as we know it. The gravitational forces would tear apart any solid structure built from normal matter. The time dilation effects would make coordination and communication across even small distances nearly impossible. How could any form of life survive in such an environment, let alone thrive? The answer might require us to completely reimagine what we mean by life itself. Perhaps consciousness near black holes wouldn't be based on carbon chemistry and liquid water. Perhaps it would emerge from electromagnetic fields dancing in the twisted space-time near the event horizon, or from patterns in the flow of plasma spiraling toward destruction. Perhaps the distinction between organism and machine would become meaningless when both need to be constructed from exotic matter that can withstand forces that atomize ordinary substances. if such civilizations exist. They operate on time scales and energy scales so vast that our entire recorded history, from the first cave paintings to the present moment, would represent less than a heartbeat in their experience. While we measure progress in decades and centuries, they might think in terms of millions or billions of years. How would we even recognize such beings if they existed? How do you detect civilizations that manipulate objects where time passes at different rates? Where signals take years to travel between different parts of their infrastructure, where their technology operates according to physical principles we haven't yet discovered. The search becomes even more complex when you realize that the signals we might receive could be stretched or compressed by the same gravitational effects that power their civilization. Radio waves climbing out of deep gravity wells become redshifted to lower frequencies. Light becomes bent and focused in ways that could either amplify or hide evidence of their existence. This exploration isn't just an intellectual exercise about imaginary aliens. It's a journey into the fundamental limits of what complexity and intelligence might achieve in our universe. It forces us to confront the boundaries of our own understanding and to question basic assumptions about what's possible. Every step of this investigation will reveal something unexpected about the nature of reality itself. We'll discover that our intuitions about space, time, matter, and energy are artifacts of our limited experience. We'll find that the universe contains possibilities that are both more beautiful and more strange than anything we've yet imagined. But perhaps most importantly, we'll begin to understand our own place in this cosmic hierarchy. We are beings capable of contemplating black holes, even though we evolved on the surface of a relatively calm planet orbiting a stable star. We are matter that has organized itself into patterns complex enough to understand, at least partially, the deepest mysteries of space-time itself. To truly understand what civilizations might accomplish with these cosmic monsters, we first need to comprehend what black holes actually are. And that understanding begins with confronting a definition that challenges everything your common sense tells you about reality. A black hole is a region in space where gravity has become so overwhelmingly intense that nothing, not matter, not energy, not even light itself, can escape once it crosses a certain boundary. Imagine trying to throw a ball so hard that it never comes back down. On Earth, you'd need to throw it at about 11 kilometers per second to achieve escape velocity. Near a black hole, that escape velocity exceeds 300,000 kilometers per second, the speed of light itself. This creates what can only be described as a hole in the fabric of space-time. Not a hole you could fall through to somewhere else, but a region where the normal structure of reality becomes so warped that it essentially tears away from the rest of the universe. But how does such an impossible object come into existence? Picture a star. Not just any star, but a massive giant containing 25 times more material than our Sun. For millions of years, this stellar behemoth burns with nuclear fury in its core, converting hydrogen to helium and releasing enough energy to support its enormous bulk against the crushing force of its own gravity. It's a delicate balance, outward pressure from nuclear reactions exactly counteracting the inward pull of gravitational collapse. Then, inevitably, the fuel runs out. When a star of this size exhausts its nuclear fuel, catastrophe follows within seconds. Without the outward pressure of fusion reactions, gravity wins absolutely. The entire stellar core, containing more mass than our Sun, collapses from a sphere larger than Earth to a point smaller than Manhattan in less time than it takes you to blink. The outer layers, suddenly finding nothing beneath them to stand on, crash inward at speeds of 30, kilometers per second before rebounding in a supernova explosion that briefly outshines an entire galaxy. What remains is something that shouldn't be able to exist according to our everyday understanding of matter and space. All that stellar material, 25 times the mass of our Sun, compressed into a region so small that it has, for all practical purposes, no size at all. Around this impossibly compressed core lies the event horizon. Think of it as an invisible sphere marking the point of no return. It's like standing at the edge of an infinite waterfall, where every current flows downward and no path leads back to safety. Once you cross this boundary, the curvature of space-time itself becomes so extreme that every possible direction leads inward toward the central singularity. The mathematics describing this boundary are precise, but the reality is almost impossible to visualize. For a typical stellar black hole containing about 10 solar masses, the event horizon forms a sphere with a radius of roughly 30 kilometers. That's smaller than most cities, yet it marks the edge of a gravitational prison from which not even light can return. All that mass, 10 times the entire Sun, isn't actually spread throughout that sphere. According to our best understanding, it's all concentrated at the very center, in a singularity with literally zero size but finite mass. Black holes come in different sizes, and the scale differences are staggering. Stellar black holes, formed from the collapse of massive stars, typically contain between 3 and 100 solar masses. Intermediate black holes contain hundreds to hundreds of thousands of solar masses, and then there are the supermassive black holes, containing millions or even billions of times the mass of our Sun, that lurk at the centers of galaxies. In 2020, astronomers achieved something that seemed impossible just decades earlier. They actually photographed the event horizon of a supermassive black hole. Using a network of radio telescopes spanning the entire Earth, the Event Horizon Telescope captured an image of Sagittarius A star, the 4.3 million solar mass black hole at the center of our own Milky Way galaxy. That photograph showed a glowing ring of superheated gas surrounding a dark central region. The darkness wasn't empty space, it was the event horizon itself, a region where space-time curvature had become so extreme that it bent light into orbits around the central mass. What makes black holes truly alien is their simplicity. According to physicist John Wheeler's no-hair theorem, a black hole can be completely described by just 3 properties: its mass, its electric charge, and its rotation. Everything else about the original star, its chemical composition, its magnetic field, its internal structure, disappears completely when the event horizon forms. When matter approaches a black hole, it rarely falls straight in. Instead, it typically spirals inward, forming what astronomers call an accretion disk. As this material orbits closer to the event horizon, it accelerates to tremendous speeds and heats up through friction to temperatures exceeding 10 million degrees Celsius, hotter than the cores of the most massive stars. At these temperatures, the gas doesn't just glow, it screams energy across the entire electromagnetic spectrum. The efficiency of this process is staggering. Nuclear fusion converts only about 0.7% of mass into energy. But matter falling into a black hole can convert up to 42% of its mass into pure energy, making accretion disks the most efficient power sources in the known universe. Some black holes produce jets of material streaming away from their poles at 99.9% of the speed of light. These relativistic jets can extend for thousands of light years, carrying the energy of billions of suns and creating some of the most luminous objects in the universe. Einstein's theory of general relativity describes gravity not as a force, but as curvature in the fabric of space-time itself. A black hole is like a bowling ball placed on a stretched rubber sheet. It creates such a deep depression that nearby objects naturally roll toward it. But black holes curve not just space, but time as well. This temporal distortion creates effects that seem like science fiction, but are measurable reality. Clocks run slower in stronger gravitational fields. Near a black hole, this effect becomes extreme. If you could somehow survive at the edge of the event horizon, 1 second of your experience could correspond to years for distant observers. In 1974, Stephen Hawking discovered that black holes aren't completely black. They actually emit a faint radiation and slowly evaporate. This Hawking radiation is incredibly weak. A black hole with the mass of our Sun would take 10⁻⁶7 years to evaporate completely, a time span so vast that it makes the current age of the universe look like an instant. The tidal forces near black holes create another seemingly insurmountable barrier to survival, because gravity weakens rapidly with distance. The difference in gravitational pull between your head and feet would be enormous near a black hole. This differential force would stretch your body vertically and compress it horizontally in a process physicists grimly call spaghettification. Yet even these deadly objects might hold keys to unlimited energy. Physicist Roger Penrose discovered that rotating black holes have a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. In this ergosphere, it's theoretically possible to extract energy from the black hole's rotation through a process that could recover up to 29% of the black hole's total mass energy. Most black holes are discovered through their gravitational effects on nearby objects. When a black hole orbits a normal star in a binary system, it strips material from its companion, creating the telltale X-ray signature of an accretion disk. In 2015, the LIGO Observatory detected ripples in space-time itself, gravitational waves produced by the collision of 2 black holes. These waves are so subtle that they stretch and compress space by less than 1/10,000th the width of a proton. Yet they can be detected across distances of millions of light-years. The supermassive black holes at galactic centers actively shape the evolution of entire galaxies. Their jets and winds can either trigger new star formation or shut it down entirely by blowing gas out of the galaxy. At the very foundations of physics, black holes force us to confront the limits of our current theories. The singularities at their centers represent points where our mathematical descriptions of reality break down completely. Density becomes infinite, and the distinction between space and time loses all meaning. Everything about black holes seems fundamentally hostile to life as we know it. The radiation environment would sterilize any organic molecules instantly. The gravitational forces would tear apart any solid structure made from ordinary matter. The time dilation effects would isolate any potential inhabitants from the rest of the universe. Yet these same properties that make black holes seem utterly inimical to life also make them the most powerful energy sources in the cosmos. Standing at the edge of our current understanding, we can begin to glimpse why sufficiently advanced civilizations might be drawn to these cosmic monsters despite their obvious dangers. But to truly appreciate the possibilities, we need to understand how astronomers first discovered these impossible objects and began to realize their extraordinary potential. In 1971, something happened that fundamentally altered our conception of what the universe contains. Astronomers studying X-ray emissions from the constellation Cygnus identified a source designated Cygnus X1, a powerful emitter of high-energy radiation locked in orbit with a blue supergiant star. What they observed defied explanation through conventional stellar physics. The invisible companion was pulling material from its visible partner, creating an accretion disk so hot it glowed in X-rays, yet it was far too massive and compact to be a neutron star. For the first time in history, scientists were forced to accept that black holes, objects so extreme they had previously existed only in the realm of theoretical physics, were not just mathematical curiosities, but actual features of our universe. This single discovery opened a door to recognizing phenomena that operate beyond anything we had previously imagined possible. But Cygnus X1 was just the beginning. As our telescopes became more sensitive and our techniques more sophisticated, we began to detect objects that made even stellar black holes seem modest by comparison. Deep in space, billions of light years away, astronomers found point sources of light that outshone entire galaxies. Objects so luminous they could be seen across cosmic distances that span most of the observable universe. These quasars, as they came to be known, represent the most energetically powerful phenomena we've ever observed. A typical quasar emits the energy equivalent of trillions of suns, all concentrated into a region smaller than our solar system. To put this in perspective, if a quasar were placed 33 light-years from Earth, roughly 8 times the distance to the nearest star, it would appear as bright as our sun in the sky, while simultaneously sterilizing our planet with radiation. The energy source powering these cosmic lighthouses gradually became clear through decades of observation. At the heart of each quasar lies a supermassive black hole, typically containing millions or billions of times the mass of our sun, actively feeding on the surrounding material. As matter spirals toward the event horizon, it forms accretion disks that reach temperatures of hundreds of millions of degrees, converting mass to energy with an efficiency that makes nuclear fusion look primitive. The numbers are staggering. A moderately active quasar consumes material equivalent to about 10 Earth masses every year, converting roughly 42% of that mass directly into energy through gravitational acceleration. This efficiency is 60 times greater than the nuclear fusion that powers stars, representing the most effective energy conversion process known to physics. Perhaps even more remarkable are the structures these objects create. Some quasars produce jets of material that extend for millions of light years, distances so vast that light itself takes 5 million years to travel from one end to the other. These jets, accelerated to 99.9% of the speed of light by magnetic fields twisted around rotating black holes, suggest that these objects can organize matter and energy on scales that dwarf entire star clusters. Think about that for a moment. We're looking at natural phenomena that manipulate matter across distances comparable to the gaps between galaxies, creating structures that remain coherent and directed over millions of light years. If intelligence could learn to harness and control such mechanisms, it would possess engineering capabilities that operate on galactic scales. Even our own galaxy's central black hole, Sagittarius A star, has demonstrated capabilities that border on the fantastic. Astronomers have observed it hurling entire stars out of the galactic center at speeds exceeding 5,000 kilometers per second, fast enough to escape the Milky Way entirely. These hypervelocity stars represent stellar mass objects being manipulated like projectiles by gravitational forces, suggesting that supermassive black holes can function as cosmic catapults capable of relocating stars across intergalactic distances. In September 2015, humanity achieved another breakthrough in understanding these objects when the LIGO gravitational wave detectors recorded their first signal. The instruments detected ripples in space-time itself, created 1.3 billion years ago when two black holes, one containing 29 solar masses, the other 36, spiraled into each other and merged in a cataclysmic collision. in the final fraction of a second before merger. These two objects released more energy in gravitational waves than all the stars in the observable universe were producing in light at that same moment. The collision converted 3 solar masses worth of matter into pure gravitational radiation, creating distortions in space-time that LIGO could detect as vibrations smaller than 1/10,000th the width of a proton. But it's not just the raw power that makes black holes fascinating. It's the exotic physics that emerges in their vicinity. The magnetic fields surrounding active black holes reach intensities of 10,000 a Tesla, roughly 200 million times stronger than Earth's magnetic field. These fields organize infalling matter into complex structures spanning thousands of kilometers, creating natural particle accelerators that operate on scales impossible to replicate in terrestrial laboratories. Near these objects, we observe phenomena that seem to violate our basic intuitions about cause and effect. Light from the accretion disk doesn't travel in straight lines. It follows curved paths through warped space-time, creating light echoes where we can observe the same flash of radiation arriving at Earth at multiple different times after bouncing off gas clouds at various distances from the black hole. These echoes allow us to map the geometry of curved space-time itself, revealing the three-dimensional structure of regions where space and time behave in fundamentally non-intuitive ways. The particle acceleration that occurs near black holes produces cosmic rays with energies that dwarf anything we can create artificially, while our most powerful particle accelerators on Earth can accelerate protons to energies of about 10^13 electron volts. Black holes routinely accelerate particles to energies exceeding 1020 electron volts, 10 million times more energetic than anything we've achieved technologically. Perhaps most remarkably, observations have confirmed that rotating black holes actually drag space-time itself along with their rotation. This frame-dragging effect forces nearby objects to orbit in the same direction as the black holes spin, regardless of their initial trajectory. It's as if the black hole creates a whirlpool in the fabric of reality itself, pulling everything in its vicinity into its rotational flow. The discovery of binary black hole systems has revealed that these objects can form stable, complex gravitational configurations. Two stellar mass black holes can orbit each other for billions of years, gradually spiraling closer as they radiate energy in gravitational waves, until they finally merge in explosions that shake the foundation of space-time across cosmic distances. Some black holes vary their energy output on timescales of minutes, indicating that physical processes are occurring within a few light minutes of the event horizon. Regions where time dilation effects are so extreme that minutes of local time correspond to hours or days for distant observers. This suggests that we're observing phenomena operating in environments where time itself flows at rates dramatically different from our terrestrial experience. When neutron stars collide near black holes, they create kilonovas, explosions that synthesize most of the heavy elements in the universe while simultaneously producing gravitational waves detectable by our instruments. These events demonstrate that black holes don't just consume matter. They participate in cosmic processes that create and distribute the very elements that make complex chemistry possible. The gravitational lensing effects of black holes transform them into natural telescopes of extraordinary power. Their immense gravity bends light from distant galaxies, magnifying and focusing it in ways that allow us to observe objects that would otherwise be too faint to detect. Some black holes can amplify the light from background galaxies by factors of thousands, effectively functioning as cosmic magnifying glasses that extend our observational reach deep into the early universe. Advanced spectroscopic techniques have revealed that some black holes spin at nearly the maximum rate allowed by physics. their equators moving at 150,000 kilometers per second, roughly half the speed of light. At these rotation rates, the ergosphere, the region where space-time is dragged along by the black hole's spin, extends far beyond the event horizon, creating zones where energy extraction through the Penrose process becomes theoretically possible. One of the most intriguing discoveries about supermassive black holes is their tight correlation with the galaxies that host them. Regardless of galactic size or type, the central black hole consistently contains about 0.1% of the mass of the galactic bulge surrounding it. This precise relationship suggests that black holes and galaxies grow together through some form of feedback mechanism, with each influencing the other's development over cosmic time. Detailed observations of rotating black holes have confirmed the existence of multiple event horizons. Black holes possess both an outer horizon and an inner horizon, creating distinct regions with fundamentally different physical properties. The space between these horizons represents a region where the normal relationships between cause and effect become ambiguous, and where theoretical physicists predict that closed time-like curves, paths through space-time that loop back to their own past, might become possible. Recent observations have provided evidence for energy extraction from rotating black holes through natural processes. Material orbiting in the ergosphere can gain energy from the black hole's rotation, emerging with more energy than it possessed when it entered. This confirms that the theoretical Penrose process isn't just mathematical speculation. It's a real physical phenomenon occurring around rotating black holes throughout the universe. Perhaps most mysteriously, some quasars exhibit variations in their light output that follow surprisingly regular patterns. While most scientific explanations for these patterns involve natural astrophysical processes, the mathematical precision of some observed periodicities has led to speculation about whether sufficiently advanced civilizations might be capable of manipulating quasar emissions for purposes we can't yet imagine. Though natural explanations remain far more likely, the very fact that such speculation can be taken seriously by professional astronomers indicates how exotic these objects truly are. Standing here at the threshold of the 21st century, our observations suggest that black holes possess properties and capabilities that transcend every category of our previous physical experience. They demonstrate engineering possibilities that operate across galactic distances, timescales that span millions of years, and energy densities that approach the fundamental limits allowed by physics. These aren't just theoretical curiosities. They're observable phenomena occurring throughout our universe right now, suggesting technological possibilities that extend far beyond anything achievable through conventional stellar engineering. But to understand why advanced civilizations might inevitably turn to black holes, we need to examine the fundamental relationship between civilization and energy consumption. Right now, at this very moment, human civilization consumes approximately 18 terawatts of power. That's 18 trillion watts flowing continuously through our global infrastructure, powering cities, factories, transportation networks, and the countless devices that define modern life. It sounds like an enormous number, and by historical standards, it represents an incredible achievement. But here's what puts our energy consumption in perspective: that 18 terawatts represents only 0.73% of the solar energy that strikes Earth's surface. We are, according to astronomer Kardashev's classification system, a Type 0.73 civilization, not even advanced enough to harness the full energy potential of our own planet. The Kardashev Scale provides a framework for understanding the energy requirements of truly advanced civilizations. A Type Ti civilization would control approximately 10-16 watts, roughly equivalent to capturing all the solar energy that reaches Earth. This would require revolutionary advances in fusion power, vast arrays of space-based solar collectors, and energy distribution networks that span continents. To put this in human terms, if our current global energy consumption were represented by a single light bulb, a Type 1 civilization would control the equivalent of 550,000 such bulbs burning continuously, every second of every day. They would harness energy equivalent to what our entire species currently uses in about 6 days. But Type 1 represents only the first step. A Type 2 civilization would consume approximately 10.26 watts, the entire energy output of a star like our Sun. This level of consumption would require constructing megastructures capable of intercepting and utilizing stellar radiation on a scale that makes our largest engineering projects look like children's toys. The numbers become almost incomprehensible at this scale. Our Sun produces 3.8 1026 watts continuously, converting 4 million tons of matter into pure energy every second through nuclear fusion. A Type 2 civilization would need to capture and utilize this entire output, requiring structures that encompass the entire solar system and coordinate energy flows across distances measured in astronomical units. Such a civilization might construct what physicist Freeman Dyson proposed as Dyson spheres, vast swarms of energy-collecting satellites surrounding their star, intercepting and converting stellar radiation into usable power. These wouldn't be solid shells, which would be structurally impossible, but rather millions or billions of independent collectors working in coordination to harvest stellar energy. But even stellar energy has limits. A Type 3 civilization would require approximately 1036 watts, the energy output of an entire galaxy containing 100 billion stars. This represents a jump of 10 billion times beyond Type 2 consumption, necessitating energy sources that transcend anything achievable through conventional stellar engineering. This is where black holes enter the picture as the ultimate energy sources. A typical stellar black hole, actively feeding on surrounding material, can produce approximately 10 to 31 watts through its accretion disk. That's 100,000 times more powerful than our Sun. The physics underlying this incredible energy output stems from the extreme efficiency with which gravitational acceleration converts matter to energy. When matter falls into a black hole, it can convert up to 42% of its rest mass directly into energy through the accretion process. Compare this to nuclear fusion, which converts only 0.7% of mass to energy, and you begin to understand why black holes represent the most efficient power sources in the known universe. They're 60 times more efficient than the nuclear reactions that power stars. The theoretical maximum energy extraction comes through the Penrose process, which can recover up to 29% of a black hole's total mass energy by exploiting its rotation. This isn't science fiction. It's a consequence of the strange physics of rotating black holes, where objects entering the ergosphere can gain energy from the black hole's spin. The timescales involved in black hole energy extraction dwarf anything we typically consider. While constructing megastructures around black holes might require thousands or millions of years using advanced automation, once operational, these systems could provide energy for trillions of years. A main sequence star like our Sun burns for roughly 10 billion years. A black hole could theoretically be exploited for energy over timescales that are thousands of times longer. Yet despite the obvious advantages of such massive energy consumption, we observe a curious fact about our universe. Despite decades of searching with increasingly sensitive infrared telescopes, astronomers have found no confirmed examples of Type II civilizations. Any civilization harvesting the complete energy output of a star would necessarily radiate waste heat detectable as infrared emissions. But the galaxy appears remarkably free of such signatures. This absence might reflect the incredible engineering challenges involved in constructing stellar-scale megastructures. Solid Dyson spheres are physically impossible due to material strength limitations. No known material could support a structure large enough to surround a star. More realistic designs involve swarms of independent collectors or stationary bubbles of energy-harvesting satellites. The thermodynamics of such systems create unavoidable signatures. Any energy collector must obey the laws of thermodynamics, meaning it must radiate waste heat at lower temperatures than the energy it collects. This creates distinctive infrared signatures that should be detectable across galactic distances if Type II civilizations exist in significant numbers. But perhaps the absence of Type II signatures reflects something more profound about the path of technological development. Perhaps sufficiently advanced civilizations skip the stellar phase entirely and move directly to black hole energy extraction, recognizing that stellar energy sources are fundamentally limited by both power output and operational lifetime. Consider the advantages. While a main sequence star produces energy for roughly 10 billion years, black holes can be exploited for energy extraction over trillions of years. Even after all the stars in the universe have exhausted their fuel and died, black holes will continue to exist, making them the only long-term energy sources available in the far future. The engineering challenges of black hole energy harvesting are extreme, but not necessarily impossible. The key is finding the gravitational habitable zone, the region around a black hole where tidal forces are manageable but energy extraction remains viable. For stellar black holes, this zone typically extends from about 10 to 100 Schwarzschild radii from the event horizon. Closer than 10 Schwarzschild radii, tidal forces become destructive to any conceivable structure. Further than 100 Schwarzschild radii, the energy density drops significantly, reducing the efficiency of collection systems. But within this zone, advanced materials and engineering might allow the construction of energy harvesting infrastructure. The power carried by relativistic jets from active black holes represents another potential energy source. These jets transport approximately 1029 watts across distances of thousands of light years. Sufficiently advanced civilizations might construct interceptor arrays positioned along these jets, harvesting energy from particles traveling at 99.9% of the speed of light. Different types of compact objects offer different advantages for energy extraction. Pulsars, rapidly rotating neutron stars, can produce up to 10 pl 28 watts through electromagnetic radiation. Colliding neutron stars release 10 Tal 32 watts instantaneously, but these events are brief and unpredictable. Black holes offer the optimal combination of high power output and long-term stability. A truly galactic civilization, Type III on the Kardashev Scale, would need to coordinate energy extraction from hundreds or thousands of black holes distributed throughout their galaxy. This would require communication and coordination networks spanning tens of thousands of light years. With signal delays measured in millennia, the cosmic hierarchy of energy sources follows a clear progression. Planetary energy sources provide about 10,016 watts, stellar sources about 10,026 watts, black holes up to 10,031 watts, entire galaxies around 10,036 watts, and galaxy clusters up to 10,039 watts. Each step represents a jump of thousands to millions of times more energy. But the fundamental limitations of matter itself present ultimate constraints. Known materials cannot support solid structures larger than a few kilometers in gravitational fields of the strength found near black holes. Any megastructures would need to rely on exotic materials with properties we haven't discovered, or perhaps on magnetic and gravitational field manipulation rather than conventional structural engineering. The physics of energy collection in extreme environments pushes every known boundary. Collectors would need to operate at temperatures of millions of degrees while resisting radiation levels that would vaporize any conventional materials. They would need to function in magnetic fields hundreds of millions of times stronger than Earth's, while maintaining structural integrity across distances measured in thousands of kilometers. The electromagnetic environment near active black holes resembles nothing in our terrestrial experience. Charged particles accelerated to near light speed create radiation levels that would destroy electronic systems instantly. Magnetic field strengths reach values that would levitate and tear apart any magnetic materials. Temperature gradients span millions of degrees across relatively short distances. Yet these same extreme conditions that make black holes seem impossible for conventional engineering also represent the ultimate energy frontier. Beyond black hole energy extraction, only the theoretical manipulation of vacuum energy, drawing power from the quantum fluctuations of empty space itself, could provide greater energy densities. Standing at our current type 0.73 level, contemplating the engineering requirements for black hole energy harvesting feels like trying to understand quantum mechanics while armed only with stone tools. The gap between our current capabilities and what would be required spans not just technological development, but fundamental advances in our understanding of physics, materials science, and the nature of space-time itself. But perhaps that gap, however vast, represents not an insurmountable barrier, but simply the next phase in the evolution of intelligence in the universe. And if we imagine civilizations that have crossed that threshold, we must confront the staggering engineering challenges of actually constructing mega-structures around black holes. Picture, if you can, a Dyson sphere reimagined for the most extreme gravitational environment in the universe. Instead of orbiting peacefully around a star at the comfortable distance of Earth's orbit, these energy collectors would need to operate between 50 and 200 kilometers from a black hole's event horizon, a region where space-time itself becomes so warped that our normal understanding of physics reaches its breaking point. The materials required for such construction would need properties that make our strongest substances look like tissue paper. Steel has a tensile strength of about 400 million pascals. The gravitational stresses near a black hole would require materials with strength measured in trillions of times that value. We're talking about structures that could support the equivalent weight of entire continents, while operating in gravitational fields that fluctuate by millions of g-forces across their length. But material strength represents only the beginning of the challenges. The orbital mechanics near black holes follow rules that make conventional satellite deployment impossible. Orbits close to the event horizon are inherently unstable. Tiny perturbations that would be insignificant around a normal star cause satellites to spiral inward toward destruction within minutes or years. Any collection system would require continuous thrust to maintain its position, consuming energy even while trying to harvest it. The most exotic energy source these megastructures might tap is Hawking radiation itself. While a stellar mass black hole emits only about 10 to 28 watts through this quantum process, roughly equivalent to the power consumption of a small household appliance, Collectors with surface areas comparable to continents could potentially harvest enough of this radiation to power advanced civilizations. The irony is profound. Using continent-sized structures to collect energy from quantum effects occurring at the edge of nothingness. Far more practical would be intercepting the relativistic jets that stream from the poles of rotating black holes. These cosmic fire hoses carry particles accelerated to 99.9% of light speed across distances measured in thousands of light years. Structures positioned along these jets, essentially cosmic nets thousands of kilometers wide, could harvest energy from matter moving at velocities we can barely achieve with our most advanced particle accelerators. The Penrose process offers perhaps the most elegant approach to black hole energy extraction. Automated machinery could continuously launch material into the ergosphere, that strange region outside the event horizon where space-time itself is dragged along by the black hole's rotation. Objects entering the ergosphere can be split, with one part falling into the black hole while the other escapes with more energy than the original object possessed. It's like using the black hole's own rotation as a cosmic amplifier, extracting energy directly from the spin of space-time itself. Rather than massive solid structures, the most feasible designs might involve networks of millions of autonomous collectors. These satellite swarms would maintain precise formations through ion propulsion and gravitational maneuvering, creating distributed collection arrays that could adapt to the chaotic environment near a black hole. Each individual collector might be no larger than a building, but coordinated in formations spanning hundreds of thousands of kilometers. The engineering challenge of protecting these structures from tidal forces pushes the boundaries of conceivable technology. The difference in gravitational pull between the front and back of a large structure near a black hole could reach millions of Gs. Countering this would require either exotic field generators that could create artificial gravity gradients or flexible construction techniques that allow structures to stretch and compress while maintaining functionality. Getting the harvested energy away from the black hole presents its own impossibilities. Transmitting power across interplanetary distances would require focused beams of microwaves, or perhaps even gamma rays. With beam control systems capable of maintaining millimeter precision across astronomical distances. The receiving stations would need to handle power densities that could vaporize planets if the beam wandered off target. Any civilization undertaking such a project would likely construct massive habitat stations in stable orbits far from the black hole's immediate influence. These artificial worlds would receive energy via wireless transmission from the collector arrays, supporting populations that might number in the trillions. The habitats themselves would need to be mobile, capable of orbital adjustments to avoid the various hazards that populate the chaotic environment around active black holes. The materials science challenges alone require revolutionary advances beyond our current understanding. Carbon nanotubes, with strength-to-weight ratios thousands of times better than steel, might provide starting points for construction. But even these would likely prove inadequate for the extreme stresses involved. More exotic possibilities include matter made from strange quarks, nuclear matter compressed beyond the density of atomic nuclei, or materials that incorporate magnetic field structures as load-bearing elements, rather than relying solely on atomic bonds. Operating in an environment where the background temperature reaches 100 million degrees Celsius requires cooling systems that have no terrestrial equivalent. These thermal management systems would need to radiate away enormous amounts of heat while operating in vacuum conditions with radiation levels that would destroy conventional materials almost instantly. The cooling might require exotic techniques involving the controlled emission of particles or electromagnetic radiation tuned to specific frequencies. Spacecraft operating near black holes could use gravitational assists to achieve velocities approaching 10% of light speed. By carefully planned orbital maneuvers, vessels could use the black hole itself as a cosmic slingshot, extracting energy from its rotation to reach speeds that would make interstellar travel practical. These trajectories would require navigation precision beyond anything we've achieved, with course corrections timed to nanosecond accuracy to avoid falling past the point of no return. The accretion disk surrounding an active black hole would serve as a natural refinery for exotic materials. Under the extreme pressures and temperatures of infalling matter, nuclear processes create elements that cannot exist under normal conditions. Robotic miners operating in this environment could harvest gold, platinum, and hypothetical super-heavy elements formed nowhere else in the universe. The mining equipment would need to be essentially expendable, designed for single-use operations in an environment that destroys anything conventional within minutes. Communication across such a system would require techniques that compensate for relativistic effects. Signals transmitted from near the event horizon would arrive at distant receivers, heavily redshifted and time-dilated. A message that takes 1 hour to send from the collection arrays might take days to reach coordination stations in normal space. The communication protocols would need to account for the fact that simultaneity itself becomes meaningless when different parts of the system experience time at different rates. The energy abundance near black holes would make possible technologies that remain pure speculation today. Particle accelerators fed by black hole energy could produce antimatter on industrial scales, creating fuel for spacecraft capable of reaching significant fractions of light speed. The antimatter production facilities would themselves be engineering marvels, requiring magnetic containment systems that dwarf anything we've conceived. Artificial magnetic field generators would be essential for protecting the megastructures from the intense radiation environment. These would need to produce fields measured in tens of thousands of Tesla, strengths that would levitate human bodies and induce powerful electrical currents in any conducting materials. The field generators would function like cosmic umbrellas, deflecting charged particles that would otherwise sterilize any equipment or potential inhabitants. The gravitational environment near black holes would enable scientific observations impossible anywhere else in the universe. Detectors positioned in these extreme space-time curvatures could observe gravitational waves with sensitivities that make LIGO look primitive. These observatories would essentially turn the black hole itself into a gravitational lens, amplifying signals from cosmic events occurring billions of light-years away. Research facilities operating near black holes would have access to physics laboratories with conditions that cannot be replicated elsewhere. Studies of matter at nuclear densities, observations of quantum effects in strong gravitational fields, and experiments with the fundamental nature of space-time itself would be possible. These laboratories would advance our understanding of physics in ways that purely theoretical work cannot achieve. Any realistic megastructure project would require multiple redundant systems. The environment near black holes is so inherently hazardous that component failures are inevitable. Multiple independent collection arrays, backup power transmission systems, and emergency evacuation protocols would be essential. The loss of individual structures would need to be anticipated and planned for, with replacement capabilities built into the overall design. The scale of construction would dwarf every human engineering project combined. Building comprehensive energy collection systems around black holes would require resources extracted from hundreds of star systems, construction timelines measured in millennia, and coordination networks involving trillions of autonomous construction robots. The logistics of transporting materials and equipment across interstellar distances while maintaining the precise timing required for orbital construction in chaotic gravitational fields, represents an organizational challenge as daunting as the engineering problems. Each component of such a system would need to be designed, tested, and deployed with reliability standards that make our most critical spacecraft seem crude. There would be no opportunity for repairs or maintenance once components are deployed near the event horizon. Everything would need to function perfectly for decades or centuries, while experiencing stresses that would instantly destroy any technology we've ever built. Yet despite these overwhelming challenges, the potential energy return makes such projects theoretically worthwhile. A successful black hole energy extraction system could power a galactic civilization for trillions of years, providing energy densities and total outputs that dwarf every other conceivable source. The engineering challenges, however extreme, might represent simply the price of admission to true cosmic-scale civilization. But before any civilization could hope to master such engineering, they would need to confront the deeper mystery of what black holes actually represent. These objects force us beyond the comfortable boundaries of known physics into realms where our most fundamental theories begin to break down, and reality itself becomes negotiable. When Einstein developed his theory of general relativity, he discovered equations so elegant they seemed to capture the geometric essence of gravity itself. But those same beautiful equations contained a disturbing prediction. Under certain conditions, when matter becomes sufficiently concentrated, the mathematics predicts the formation of singularities. Regions where density becomes literally infinite, and the curvature of space-time diverges beyond any finite value. At a singularity, our entire framework for understanding reality simply stops working. The laws of physics as we know them cease to provide meaningful predictions. It's not that we lack sufficient computational power or experimental precision. It's that the very concepts we use to describe physical reality become undefined. Temperature, pressure, volume, even the distinction between space and time lose their meaning when confronted with infinite density. In 1974, Stephen Hawking discovered something that seemed to violate one of the most fundamental principles of quantum mechanics. If black holes evaporate by emitting thermal radiation, as his calculations suggested, then all the information that originally fell into the black hole would be lost forever when the black hole finally disappears. This creates what physicists call the information paradox. Quantum mechanics insists that information cannot be destroyed. Yet Hawking radiation appears to carry no information about the matter that created it. The time dilation effects near black holes create their own impossible scenarios. At the event horizon of a stellar mass black hole, gravitational time dilation becomes so extreme that 1 second of local time corresponds to approximately 317 years, as measured by distant observers. If you could somehow survive near the event horizon and wanted to communicate with colleagues in normal space, you could shout a single word, and by the time that sound wave reached them, they would have experienced over 3 centuries. The ergosphere of a rotating black hole presents an even stranger environment. This is the region outside the event horizon where space-time itself is being dragged around faster than light speed. Within the ergosphere, it becomes physically impossible to remain stationary relative to distant observers. The very framework of space and time compels everything to rotate along with the black hole. Objects are forced to participate in the black hole's rotation regardless of their own propulsion capabilities. Light itself behaves in impossible ways near black holes. At a distance of exactly 1.5 times the Schwarzschild radius, photons can orbit the black hole in perfect circles. creating what astronomers call the photon sphere. Light entering this orbit can circle the black hole indefinitely, creating ghostly rings of illumination that exist at the boundary between escape and capture. These circular light paths create optical effects that have no equivalent in everyday experience. An observer at the right position could theoretically see the back of their own head by looking around the black hole, as light from behind them curves all the way around the object and returns to their eyes. Quantum mechanics introduces even stranger possibilities near black holes. The extreme gravitational fields can create quantum entanglement effects that span astronomical distances. Particles that become entangled near the event horizon might maintain their quantum correlations even when separated by light years, potentially allowing for instantaneous information transfer. The frame-dragging effects of rotating black holes can create closed time-like curves, paths through space-time that loop back to their own beginning. In principle, these paths could allow information or even objects to travel backward in time, creating paradoxes where effects appear to precede their causes. Accelerated motion near black holes produces its own quantum effects. The Unruh effect predicts that observers experiencing extreme acceleration will detect thermal radiation in regions that appear as empty vacuum to unaccelerated observers. Near black holes, where acceleration can reach millions of Gs, this effect becomes pronounced enough to potentially interfere with technological operations. Recent theoretical work has proposed that the event horizon itself might not be the smooth, empty boundary that general relativity suggests. The firewall hypothesis argues that quantum effects at the horizon create a wall of high-energy radiation that would incinerate anything attempting to cross. The principle of black hole complementarity suggests something even more mind-bending. According to this idea, information falling into a black hole exists in two different states simultaneously. From the perspective of an outside observer, the information never crosses the event horizon but becomes encoded on the horizon's surface. But from the perspective of someone falling into the black hole, the information passes through normally. Both perspectives are equally valid, meaning that reality itself becomes observer-dependent. The Penrose process for extracting energy from rotating black holes requires particles with negative energy to fall into the black hole. These aren't particles made of antimatter, but rather particles that have less energy than the vacuum of empty space. The existence of such particles near black holes suggests that our understanding of energy becomes incomplete in extreme gravitational fields. Rapidly rotating black holes approach fundamental stability limits. The Chandrasekhar instability suggests that black holes spinning near their maximum rate become unstable, potentially causing them to explode in ways that could expose their singularities to the outside universe. The quantum vacuum near black holes becomes active in ways that have no analog in normal space. Virtual particle pairs can become real particles when one member falls into the black hole while the other escapes. This process creates Hawking radiation and suggests that the apparent emptiness of space near black holes conceals an active quantum foam of particle creation and annihilation. Perhaps most remarkably, the holographic principle suggests that all the information contained within a three-dimensional volume near a black hole can be encoded on the two-dimensional surface of the event horizon. This implies that what we perceive as three-dimensional reality might actually be a projection from information stored on distant boundaries, a cosmic hologram where the apparent depth of space is illusory. The entropy of black holes follows rules that contradict everything we know about thermodynamics. Jacob Bekenstein discovered that black hole entropy is proportional to the area of the event horizon, not its volume. This suggests that the fundamental nature of information storage in the universe might be two-dimensional rather than three-dimensional. Extreme gravitational fields might reveal physics beyond the standard model. Supersymmetric particles could become detectable near black holes, where energy densities approach scales where grand unification theories predict new phenomena. Alternative theories of gravity might produce observable effects that differ from general relativity's predictions. Some solutions to Einstein's equations suggest that rotating black holes might contain traversable passages to other regions of spacetime. These wormholes could connect different parts of our universe or even link to entirely separate universes, opening possibilities for transportation that transcend normal concepts of distance and causality. At the smallest scales, even our understanding of space and time breaks down completely. The Planck length represents the scale at which quantum effects of gravity become dominant. At distances smaller than this, our current theories provide no meaningful description of reality. Yet conditions near black hole singularities involve precisely these scales, suggesting that understanding black holes requires a theory of quantum gravity that we have yet to develop. Standing at the boundary between the known and unknowable, black holes represent not just exotic objects but windows into the deepest mysteries of existence itself. But to truly comprehend the role these cosmic monsters might play in the ultimate fate of intelligence, we must step back and view them not as isolated curiosities, but as the organizing principles that govern the largest structures in the universe. At the heart of our own Milky Way galaxy sits Sagittarius A star, a supermassive black hole containing 3 million times the mass of our Sun. This isn't just a passive gravitational anchor, it's an active architect that has shaped the evolution of our entire galaxy for billions of years. Through powerful jets of high-energy particles and precisely timed periods of activity, it regulates when and where new stars can form throughout the galactic disk. But Sagittarius A star, massive as it is, pales in comparison to the true giants lurking at the centers of distant quasars. In 2018, astronomers confirmed the existence of TON 618, a quasar powered by a black hole containing approximately 66 billion solar masses, roughly 15,000 times more massive than our galactic center. This single object emits energy equivalent to 140 trillion suns burning simultaneously. Think about that scale for a moment. A single black hole producing more energy than 400 billion stars combined. If a Type 3 civilization needed to harness the energy output of an entire galaxy, they might accomplish it by constructing megastructures around just one of these ultra-massive black holes, rather than attempting to capture energy from hundreds of billions of individual stars. Such a civilization would need to coordinate engineering projects spanning galactic distances. The Milky Way contains 400 billion stars distributed across a disk 100,000 light-years in diameter. Controlling energy flows on this scale would require communication networks with signal delays measured in millennia. The universe itself provides templates for organization on these scales. The cosmic web organizes matter into filaments that extend for 500 million light-years. These structures, composed primarily of dark matter, create pathways along which galaxies cluster and evolve. Advanced civilizations might use these natural superhighways as scaffolding for megastructures that span the spaces between galaxies. In approximately 4.5 billion years, we'll witness one of the most spectacular events possible in our local universe. The Andromeda Galaxy will collide with the Milky Way in a cosmic dance that will reshape both galaxies completely. When this happens, the supermassive black holes at the centers of both galaxies will eventually spiral toward each other. creating a single black hole containing roughly 100 million solar masses. The energy released during this merger will briefly outshine every other source of gravitational waves in the cosmos. Some quasars produce relativistic jets that extend for 10 million light years, distances so vast that light takes 10 million years to travel from the black hole to the end of the jet. These structures carry enough energy to power billions of Type II civilizations simultaneously. Even supermassive black holes operate within fundamental limits. The Eddington limit restricts how rapidly they can grow by consuming surrounding matter. When accretion rates become too high, radiation pressure prevents additional matter from approaching the black hole, naturally limiting growth to approximately 46 solar masses per million years. Galaxy clusters represent the largest gravitationally bound structures in the universe. The Coma cluster contains over 1.0 galaxies with a total mass equivalent to trillions of stellar mass black holes. The energy content of such structures could potentially support civilizations that operate on scales beyond individual galaxies. Yet, looming over all these vast energy sources is dark energy, which comprises 68% of the universe and acts as a repulsive force, accelerating cosmic expansion. This force grows stronger over time, eventually overwhelming gravity and preventing the formation of new, large-scale structures. The far future presents scenarios that challenge our basic assumptions about energy sources. In approximately 10 to 14 years, all stars will have exhausted their nuclear fuel and died. At that point, black holes will be the only remaining sources of energy for any surviving civilizations. But even black holes are not eternal. Stephen Hawking's calculations show that they evaporate through quantum radiation over timescales that depend on their mass. A solar mass black hole would require 10⁻⁶ years to evaporate completely, a span that exceeds the current age of the universe by a factor of 10^57. Yet this still represents a finite limit. The apparent absence of detectable Type III civilizations creates one of the most profound puzzles in astrobiology. If intelligence evolves commonly throughout the universe, and if the energy advantages of black hole engineering are as dramatic as physics suggests, why don't we observe obvious signs of galactic scale engineering? Perhaps the answer lies in the time frames involved. Even a civilization capable of near light-speed travel would require approximately 100,000 years to spread throughout a galaxy. While this seems impossibly long from human perspective, it represents only 0.007% of the universe's total age. The early universe contained primordial black holes formed during the first fraction of a second after the Big Bang. These objects, if they exist, could have masses ranging from asteroids to millions of suns. Some would be evaporating right now through Hawking radiation, potentially providing natural energy sources that require no engineering to exploit. The accelerating expansion creates its own cosmic horizon. As space expands faster than light can travel across vast distances, galaxies beyond a certain distance become permanently unreachable. This shrinking horizon gradually isolates each galaxy cluster from the rest of the universe. Truly transcendent civilizations might construct what Freeman Dyson envisioned as matryoshka brains, computational structures using black hole energy to run simulations of extraordinary complexity. These cosmic computers could potentially simulate entire universes with sufficient detail to contain conscious beings. The extended Kardashev scale pushes beyond galactic energy consumption into realms that challenge basic concepts of reality. A hypothetical Type Wafu civilization would control multiple galaxies. Type V civilizations might manipulate entire universes. Type VI civilizations would transcend physical dimensions entirely. The ultimate fate of cosmic-scale civilizations depends on the fundamental stability of matter itself. Theories predict that protons will decay over timescales of 1034 years, eventually destroying all atomic matter. Civilizations hoping to survive beyond this horizon would need to transition to pure energy-based existence. Perhaps the most speculative possibility involves treating the universe itself as a computational system. If reality emerges from information processing at quantum scales, sufficiently advanced civilizations might learn to manipulate the fundamental code that generates physical existence, effectively becoming programmers of reality itself. Standing here in our current epoch, when stars still shine and black holes offer vast reservoirs of extractable energy, we find ourselves contemplating possibilities that stretch from the merely impossible to the utterly transcendent. But perhaps the most profound revelation isn't about what these cosmic civilizations might achieve, but about what our ability to contemplate them reveals about our own extraordinary position in the cosmos. Let's begin with a moment of cosmic humility that puts everything in perspective. The entire span of human history, from our earliest ancestors developing language and tools about 300,000 years ago to this very moment, represents approximately 0.007% of the universe's total age. If the cosmos were a person celebrating their 50th birthday, all of human civilization would represent the final 11 seconds of their life. Meanwhile, civilizations capable of harnessing black hole energy might operate on timescales where our entire history appears as brief as a single heartbeat. The energy comparison is equally staggering. Right now, human civilization consumes approximately 18 terawatts of power continuously. But this enormous output represents only 0.0001% of the energy produced by a single stellar black hole's accretion disk. If the energy output of a black hole were represented by all the water in Earth's oceans, our entire global energy consumption would be equivalent to a single drop. The temporal perspective becomes even more overwhelming when stretched across cosmic time. If you compressed the entire 13.8 billion-year history of the universe into a single calendar year, human civilization wouldn't appear until 11:58:43 p.m. on December 31st, literally the final 77 seconds of the cosmic year. In this compressed timeline, civilizations that have been harnessing black hole energy might have existed since September or October, operating for cosmic months while we've been present for little more than a minute. This raises perhaps the most profound question we can ask. Are we truly alone in this vast cosmos? The Fermi paradox takes on crushing weight when viewed against these scales. If intelligence is common, if the advantages of black hole engineering are as overwhelming as physics suggests, then where is everybody? Perhaps advanced civilizations are so rare that consciousness becomes rarer than supernovas, more precious than the formation of solar systems. But here's what makes our apparent insignificance profoundly significant. The fact that you can contemplate black holes at all demonstrates something remarkable about the nature of the universe. The cosmos has evolved a mechanism for understanding itself. You are matter that has become aware of matter, energy patterns that have learned to contemplate energy. Among the trillions of species that have existed on Earth, only one has developed physics, mathematics, and the conceptual framework necessary to imagine cosmic-scale civilizations. Only humans write equations describing black hole ergospheres. Only humans build telescopes capable of observing accretion disks around distant quasars. You live during the only epoch in cosmic history when the universe is both old enough to have formed complex structures like black holes and young enough for stars to still be shining. In a few trillion years, when the last red dwarfs fade, The energy sources we've discussed will be the only remaining pools of power in an otherwise cold and empty universe. Your existence represents a cosmic accident of extraordinary precision. Earth orbits at exactly the right distance from a stable star, in a relatively quiet region of our galaxy, during an epoch of relatively low cosmic radiation. If we are indeed alone, or if intelligence is extremely rare, then we carry a responsibility that extends far beyond our species. Our technology serves as a bridge between human-scale experience and cosmic-scale phenomena. Through telescopes, we observe black holes billions of light-years away. Through mathematics, we understand physics in conditions no human will ever directly experience. These tools allow us to transcend evolutionary limitations and contemplate realities that dwarf every category of terrestrial experience. There's a profound irony in our search for advanced civilizations. The more sophisticated a civilization becomes, the less detectable it might become to observers like us. Type 3. Civilizations might use technologies so advanced that their signatures remain invisible to our instruments. Perhaps right now, advanced beings are observing our primitive radio emissions and debating whether we show signs of intelligence. Our future as a cosmic species remains unwritten, but theoretically achievable. If we continue advancing, humanity might achieve Type 1 status within 1,000 years, Type 2 within 100,000 years, and potentially begin approaching black hole engineering within 1,000,000 years. These timeframes seem impossibly long from our perspective, but they're brief moments in cosmic terms. The mathematics that describes black holes provides evidence for something remarkable. Einstein's field equations work the same way, whether describing space-time near Earth or near a supermassive black hole's event horizon. The laws of physics appear truly universal, suggesting that any intelligent civilization would eventually discover the same fundamental principles. If advanced civilizations create detailed simulations of universes, cosmic computer programs sophisticated enough to contain conscious beings, then we might be simulated entities running on computational substrates powered by black hole energy. Yet, regardless of whether we're real or simulated, the experience of consciousness remains meaningful. One of the most remarkable aspects of our era is the democratization of cosmic knowledge. Information about black holes and gravitational waves is freely available through the internet to anyone with basic education. A curious teenager with a smartphone has access to more detailed knowledge about the universe than the greatest scholars of previous centuries. Your capacity to imagine civilizations that seem utterly impossible reflects something unique about consciousness as a cosmic phenomenon. The human brain can contemplate energy sources that dwarf the output of entire stars. This suggests that consciousness represents an emergent property of matter that transcends all proportional relationships with its physical substrate. The atoms in your body were forged in the cores of dying stars. The carbon in your muscles, the calcium in your bones, the iron in your blood, all created through nuclear fusion in stellar furnaces. You are literally made of star stuff, and through consciousness, those ancient stellar processes have developed the ability to understand their own nature. If black hole civilizations exist, they likely passed through a phase similar to our current one, a period of cosmic awakening where they first discovered the true scales of their universe. They too probably experienced the humbling recognition of their small place in the vast cosmos, followed by the empowering realization that consciousness grants the ability to comprehend realities far beyond direct experience. Our journey of understanding has only begun. Comprehending black holes represents just the first step in humanity's intellectual journey toward grasping the maximum scales and possibilities of existence. Each new discovery reveals deeper layers of cosmic complexity and opens new questions that challenge our expanding understanding. Standing here at the beginning of our cosmic awareness, we find ourselves in a position of extraordinary privilege and responsibility. But perhaps more importantly, we find ourselves fundamentally transformed by the very act of contemplating these impossible civilizations. The journey we've taken together has quietly but permanently altered how we understand our place in the vast tapestry of existence. Contemplating civilizations that harness black hole energy forces us to abandon the comfortable anthropocentrism that has shaped human thinking for millennia. We can no longer place ourselves at the center of cosmic possibility, no longer assume that our current understanding represents more than the faintest glimmer of what intelligence might achieve. This transformation reveals something profound about the limitations of our cognitive architecture. Your brain evolved to track objects the size of fruits, predict animal behavior during hunts lasting hours, navigate social relationships within small groups. Yet here you are, using Stone Age hardware to process concepts about cosmic scale engineering that operates across galactic distances and geological timescales. Our technology serves as cognitive prostheses that allow us to transcend biological limitations. The Hubble Space Telescope becomes an extension of your visual cortex. Mathematical equations extend your reasoning ability, allowing you to comprehend physics in conditions no human will ever directly experience. Through these extensions, we become hybrid entities capable of contemplating realities that stretch far beyond our evolutionary origins. This hints at what might happen to intelligence as it evolves beyond our current stage. Perhaps the distinction between biological and artificial consciousness represents only a temporary phase. Advanced civilizations might transcend the boundaries between mind and machine so completely that our current categories become meaningless. The physics underlying black hole civilizations suggests that what seems impossible today becomes inevitable given sufficient time. The laws of nature permit matter to be organized in ways that extract energy from rotating space-time and manipulate gravitational fields across astronomical distances. In a universe containing trillions of galaxies, even extremely rare events become virtually certain. This transforms our relationship with possibility itself. The question shifts from, could such things exist, to why wouldn't they exist? Embracing this perspective requires intellectual humility that can be both unsettling and liberating. The moment we assume we've grasped the fundamental limits of what's possible, we stop looking for phenomena that might transcend those limits. Science emerges not as a collection of facts, but as a method for systematically transcending the limitations of direct experience. Through controlled experiments and mathematical modeling, we explore realities completely alien to anything our ancestors encountered. We study matter at millions of degrees, observe gravitational fields billions of times stronger than Earth's, and model cosmic evolution across timescales that dwarf our species' entire history. Contemplating black hole civilizations requires balancing rigorous scientific thinking with disciplined imagination. We must remain grounded in established physics while extrapolating toward possibilities that push knowledge boundaries. This process produces genuine insights precisely because it's constrained by mathematical relationships that don't depend on human assumptions. We find ourselves caught between two profound mysteries. The apparent absence of detectable cosmic scale civilizations suggests either that intelligence is far rarer than we hope, or that advanced consciousness operates through mechanisms so sophisticated we cannot recognize their signatures. If intelligence is extremely rare, consciousness becomes one of the universe's most precious, emergent properties. If intelligence is common, but transcends our detection, we may be surrounded by forms of awareness operating on scales we haven't discovered. The communication challenges facing cosmic-scale civilizations reveal new dimensions of consciousness and time. How would beings experiencing millennia as we experience years coordinate with entities on biological timescales? Perhaps advanced civilizations develop consciousness that operates simultaneously across multiple temporal scales, maintaining rapid tactical awareness while sustaining strategic thinking across geological epochs. The ethical implications of cosmic-scale power boggle the mind. Beings manipulating stellar mass energy sources would influence the evolutionary trajectory of entire worlds. Their decisions could determine whether billions of potential civilizations ever develop. Perhaps cosmic-scale engineering requires corresponding moral evolution, ethical transcendence, paralleling technological transcendence. Access to unlimited energy would transform every assumption underlying current systems. In post-scarcity civilizations powered by black holes, traditional concepts of work, ownership, and resource allocation become obsolete. The challenge shifts from managing scarcity to discovering meaning in material abundance. Such civilizations might become cosmic gardeners, nurturing consciousness development throughout the universe. If the universe exhibits increasing complexity, from particles to atoms to molecules to life to consciousness, then awareness might represent not accident, but inevitable emergent property. Consciousness could be the universe's method for understanding itself, with each new form of awareness contributing to growing cosmic self-awareness. The ultimate questions about reality's nature might remain forever beyond even cosmic-scale civilizations. The relationship between consciousness and matter, why mathematical relationships describe physical phenomena, the nature of existence itself. These mysteries might represent limits no amount of energy can transcend, yet the pursuit provides meaning that doesn't depend on final answers. The mathematical beauty underlying black hole physics suggests aesthetic principles woven into reality's fundamental structure. The elegance of Einstein's equations, quantum mechanical symmetries, unexpected connections between physical phenomena, all hint at a cosmos whose deepest principles are beautiful, not merely functional. Perhaps advanced civilizations pursue cosmic engineering not just for practical benefits, but for aesthetic experience, participating in the universe's hidden harmonies, creating structures that resonate with the mathematical music underlying existence. Understanding these possibilities creates an invitation for humanity to participate more fully in intelligence's cosmic evolution. We can choose to remain a planetary species focused on terrestrial concerns, or begin the journey toward becoming a cosmic civilization capable of star system-spanning engineering. This choice transcends technology or energy consumption. It's about embracing our potential role as conscious participants in the universe's ongoing development, contributing our unique perspective to the growing conversation between mind and cosmos that began with awareness's first stirrings. The journey we've taken together represents just the beginning of humanity's intellectual adventure into existence's deepest mysteries. And now, as this exploration draws toward its close, we find ourselves returning to where we began, to that simple morning ritual, that cup of coffee steaming gently on your table. But you're not the same person who started this journey. That cup of coffee in front of you now represents something it never could have represented before our cosmic voyage together. What once seemed like a perfectly ordinary interaction between heated liquid and ceramic now carries within it the distant but real possibility of energy cascading down from black hole megastructures across impossible distances. feeding power into transmission networks that span light years, ultimately warming the simple pleasure of your morning routine. The transformation has been subtle but irreversible. Your mind has been quietly rewired by contemplating scales that dwarf every terrestrial reference point. You can never again look at that coffee without some part of your awareness recognizing that the atoms in the ceramic mug were forged in stellar cores, that the very concept of heat connects you to accretion disks spiraling around cosmic monsters, that the simple act of stirring liquid echoes the orbital mechanics governing matter around event horizons. This is what happens when consciousness encounters the truly cosmic. Problems that seemed overwhelming just hours ago, personal anxieties, professional challenges, even global crises, become contextualized within a framework so vast that their urgency transforms into something more manageable. Not because they matter less, but because you now carry within you the perspective of geological time, of energy scales that dwarf civilizations, of possibilities that stretch across cosmic epochs. Yet paradoxically, this cosmic perspective also makes terrestrial beauty more precious, not less. Knowing that consciousness capable of contemplating black holes might be vanishingly rare in the universe makes every moment of awareness more valuable. Understanding the vast timescales across which cosmic evolution operates makes the brief flowering of human civilization seem like something worth treasuring rather than taking for granted. Your definition of impossible has fundamentally shifted during our journey together. The word no longer means violation of physical law. It now means simply beyond current technological capability. This seemingly small distinction carries profound implications for how you approach challenges, both personal and civilizational. If beings can theoretically extract energy from the rotation of space-time itself, then surely humanity can solve climate change, develop clean energy, and transcend the limitations that currently constrain our species. When you look up at the night sky now, you see something different than you did before. Each point of light represents not just a distant sun, but the potential home of civilizations operating on energy scales that dwarf our comprehension. Some of those stars might be surrounded by megastructures so vast that they collect energy equivalent to billions of our suns. Others might host beings who have solved fundamental questions about consciousness, mortality, and the ultimate purpose of intelligence in the cosmos. The strange thing is how this cosmic awareness connects unexpectedly with your daily life. The GPS navigation system that guides you through traffic works because engineers understand the same relativistic effects that distort time near black holes. The satellites orbiting Earth must account for gravitational time dilation, or their positioning would drift by miles each day. Your smartphone contains within its circuits a practical application of Einstein's equations that describe the curvature of spacetime around massive objects. These invisible connections between cosmic physics and everyday technology reveal something profound about the unity of knowledge. The mathematics that describes matter spiraling toward destruction around event horizons also enables the communication networks that connect you to friends and family. The same quantum mechanical principles that govern Hawking radiation also make possible the computer processors running the applications you use every day. If civilizations can harness energy from black holes, objects so extreme they challenge our basic understanding of reality, then the challenges facing humanity begin to seem less insurmountable and more like engineering problems waiting for sufficiently advanced solutions. Climate change becomes a question of energy technology rather than an existential threat. Resource scarcity becomes a matter of developing better extraction and synthesis techniques rather than an inevitable source of conflict. The timescales we've explored together provide a form of cosmic patience that transforms how you relate to urgency and progress. Understanding that the universe operates across billions of years, that cosmic evolution unfolds according to rhythms that make human history appear instantaneous, creates space for both immediate action and long-term perspective. You can work towards solutions, knowing that even if progress seems slow, you're participating in processes that connect to the deepest currents of cosmic development. Consciousness of the cosmic scale paradoxically makes small details more significant rather than less. A sunset becomes more beautiful when you understand that the light reaching your eyes began its journey in nuclear reactions that convert hydrogen to helium according to the same physics that powers quasar accretion disks. A conversation with a friend becomes more meaningful when you recognize that consciousness capable of language and abstraction might be among the universe's rarest and most precious emergent properties. As perhaps the only known species capable of contemplating black holes, humanity carries a responsibility that extends far beyond our planet or even our solar system. We are the universe's current mechanism for understanding itself. The cosmos thinking about its own structure and possibilities through the neural networks of human brains. This responsibility isn't a burden, but an honor. We get to serve as consciousness, exploring the deepest questions about existence itself. Each child learning basic physics is potentially developing the mental tools necessary for comprehending cosmic-scale civilizations. When a student first encounters Einstein's famous equation, E=mc², they're acquiring a conceptual framework that connects the mass-energy equivalence in their pencil eraser to the processes that power the most luminous objects in the universe. Education becomes a form of cosmic exploration, gradually expanding human awareness towards scales that transcend direct experience. Perhaps most remarkably, this knowledge about black holes and cosmic civilizations is now democratically available to anyone with internet access. A curious person in any corner of the world can pull up detailed information about event horizons, accretion physics, and gravitational wave detection on their smartphone. The most profound insights about the nature of reality are being democratized in ways that would have been unimaginable just decades ago. Your conversations about humanity's future now necessarily include possibilities that were pure science fiction when your parents were born. Discussions about technological development, energy resources, and our species' long-term prospects operate within frameworks that encompass stellar engineering, galactic colonization, and energy extraction from objects where space-time itself becomes a medium for manipulation. Progress itself takes on new meaning when measured against the theoretical capabilities of cosmic-scale civilizations. Advances in fusion energy, space exploration, and artificial intelligence become waypoints along a trajectory that might eventually lead to the engineering marvels we've contemplated together. Each technological breakthrough represents a step toward capabilities that currently seem impossible, but are permitted by the fundamental laws of physics. Understanding cosmic possibilities makes pessimism intellectually difficult to sustain. When you grasp that the universe contains energy sources capable of powering civilizations for trillions of years, that consciousness has potentially billions of years to solve current problems. That intelligence might eventually transcend every limitation that currently constrains it. Present difficulties begin to seem temporary rather than permanent, not because solutions are guaranteed, but because possibility space is so vast that paths forward almost certainly exist. The mathematics running on your home computer carries within it the same logical structures that describe the behavior of matter near black hole event horizons. The algorithms processing your digital photos operate according to principles that connect your everyday technology to the deepest questions about space-time geometry. Your coffee table supports not just a ceramic mug, but computational devices that bridge human-scale experience with cosmic-scale physics. Each day offers renewed opportunities for cosmic contemplation. The morning light streaming through your window traveled 93 million miles from nuclear reactions that operate according to the same physics governing energy extraction from black hole accretion disks. The evening stars visible above your neighborhood include objects whose gravitational fields might be harvested by engineering projects that span light years. Every moment contains connections to scales and possibilities that stretch toward the infinite. Children being born today might live to witness the first confirmed detections of artificial megastructures around distant stars. They might see evidence of civilizations that have graduated from planetary energy sources to stellar ones, or even discover signs of engineering projects that operate around black holes themselves. The universe they inherit will be one where humanity knows that consciousness can contemplate possibilities that seemed absolutely impossible just generations earlier. Our current understanding represents only the first chapter in what will likely be an infinite story of discovery about the nature of cosmic reality. Each generation will probably encounter phenomena that stretch their conception of what's possible, just as black hole civilizations have stretched ours. The journey of cosmic awareness has no final destination because the universe appears to contain depths of complexity and beauty that exceed any finite mind's capacity to fully encompass. And yet the coffee still swirls as you stir it. Steam still rises in patterns that dissipate as quickly as they form. Warmth still transfers from liquid to ceramic to your hands in accordance with the same thermodynamic laws that govern energy flows around the most exotic objects in the universe. What has changed is not the phenomenon itself, but your understanding of how that apparently simple interaction connects to possibilities more extraordinary than any science fiction has dared imagine. This is the gift of cosmic perspective, not that it removes you from ordinary life, but that it reveals the extraordinary nature of what seemed ordinary. You remain human in scale and biology, but you now carry within your consciousness an awareness that connects morning coffee to black hole physics, daily routines to cosmic evolution, terrestrial existence, to possibilities that stretch across the vast spaces between galaxies. You are simultaneously smaller and larger than you were when this journey began, smaller in the context of cosmic scale, larger in the scope of what your mind can encompass. You remain precisely who you were, but you now know that being human means being part of the universe's ongoing project of understanding itself through consciousness that emerged from stellar death and planetary formation and biological evolution across billions of years. That cup of coffee represents the same simple pleasure it always did. But now you know that simplicity itself is the most sophisticated thing in the universe. If you're still awake, it's because the content was really good. So, take a moment. Leave a like and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.